Noctilucent Clouds. For observers at mid-northern latitudes, summer nights remain bathed in bright twilight, hampering most forms of astronomical observation. These mild summer nights can be a joy for amateur observers, however. Deep sky observing and even the aurora are washed out to insignificance due to nautical twilight persisting all night long. However, all is not lost, as summer nights bring with them a different kind of phenomena. If you are located between latitudes 50 degrees and 65 degrees north or south of the equator, then you will be graced by the presence of Noctilucent Clouds, or NLCs for short. The NLC season typically runs from late May until early August in the Northern Hemisphere, and December to January for Southern Hemisphere observers. However, sightings outside this latitude window have been recorded with ever greater frequency in recent years. Since my own early sightings, I have been determined to observe every NLC display that appears each summer period in the hope of gaining more proficiency with my observations and a better understanding of their appearance, frequency and movement by gaining as much experience as I can, along with maintaining a dedicated photographic record of all displays which appear over Northern Ireland. My own introduction to NLCs began many years ago when I accidentally encountered these eerie glowing clouds at the end of my summer comet hunting sessions in the hours before dawn. I recall feeling mesmerised by the beautiful structure and colours they contained and knew deep down that this phenomena was something very special indeed. At the time I did not realise what they were or their true importance. However, in due course, as my curiosity became heightened, I gradually began researching through various books and astronomy magazines to get some understanding of what was going on and how to go about observing them. I was fortunate enough at the time to befriend a veteran NLC observer with over 30 years of NLC experience under his belt at my local astronomical society, who has since developed my interest in NLCs to a high level. His name is John C. McKenna, and in the years to come we will be swapping countless text messages and phone calls discussing these amazing clouds. The summer of 2005, and in particular 2006 and 2009, produced the best displays I have ever seen. I never realised that nature could produce such beautiful artwork in the sky. Each display was unique, and the best of them covered much of the entire sky with breathtaking colours. These were unforgettable sights. If you have never seen a bright, complex, Noctilucent cloud display before, then be prepared to be amazed. These clouds promise you a profound visual experience, and once you have seen a good one, then the chances are that you will be hooked for the rest of your life, just as I have. Warning: be prepared to miss out on a lot of sleep. Genesis of the Noctilucent Clouds. NLCs bear little resemblance to normal clouds which form within the troposphere. That's a region of the Earth's atmosphere located some 14 kilometres or 9 miles high. This low altitude results in our weather clouds appearing dark against the summer twilight sky, as they reside within the Earth's shadow, hidden from the sun's glare. Noctilucent is a Latin derivative which loosely translates as night shining, and shine they do. The term Noctilucent Clouds was probably first coined by O. Jesse, who was then active at the Berlin Observatory, making the first photographic measurements of the clouds. When the sun was between 6 and 16 degrees below the horizon, the NLCs, which are located at a height of some 82 kilometres within the Mesosphere, are illuminated by sunlight when they then become visible to ground-based observers. Very little is known about NLCs even today. In fact, the details of modern NLC science could be presented on the back of a postcard. Okay, that's a slight exaggeration, but the field is still open to much research to come. These clouds are mysterious in the extreme, and observations and images are sought after by researchers making this field of astronomy and meteorology one of the few areas where amateur observers can contribute to science. The genesis of the Noctilucent Clouds are as elusive as the clouds themselves, and theoretical at best. However, a popular and plausible belief among researchers suggests that NLCs are made up of meteoritic dust particles encased in ice crystals. These ice crystals, which contain dust particles from meteoroids, comets and asteroids, are so small that their size is likened to the particles in cigarette smoke. NLC ice crystals are so transparent that they only reflect 1 in 1,000th of the incident sunlight they receive, hence why their tenuous profile is never seen in the daytime sky. NLCs are very thin. Measurements have suggested their optical thickness is in the region of 10 to 4 nanometers, with cloud particles in the range of 50 nanometers. The mesosphere, where the NLC particles reside, experiences a freezing temperature of minus 100 degrees Celsius. Here, there's very little water. However, at this temperature, any molecules of water which do form will rapidly turn to ice and encase any dust particles, which act as a seed, where the process of nucleation induces the NLC to drop by several kilometers to the altitude in which they are normally seen, and that's about 80 to 100 kilometers above sea level. The coldest temperatures in the mesosphere form over the Earth's polar regions during the summer months, which explains why NLCs are only seen at this time of year. Some researchers suggest the presence of NLCs are an indicator of global warming. The reason being that increased temperatures at lower altitudes results in decreased temperatures in the mesosphere, inducing the process of nucleation and hence NLC formation. Much further information using modern ground-based observations, historical observations and science gathered from the new AIM satellite launched back in 2006 will shed new light into NLC formation. For now, NLCs remain as exciting and as mysterious as they always have been. Historical sightings. It is well known that the first observation of NLCs was made by Thomas W. Backhouse in 1885, fully 2 years after the violent 1883 eruption of the volcano on Krakatoa Island. This was a tsunami-generating event which completely destroyed the island itself and sent immense concentrations of volcanic ash into the upper atmosphere, which is thought by many to be the progenitor event that led to the formation of NLCs, which began to manifest with more frequency after the event. Here are several images of Thomas W. Backhouse himself. These were supplied to me from the historical research by John C. McConnell from Northern Ireland, so a big thank you to John for sending over these images from his research. However, more recent studies suggest the event was not responsible for their formation at all. Garsden and Schroeder in a 1989 paper debated on why there were no sightings of NLCs prior to 1885 and suggested that the eruption was significant because it had alerted observers to make several careful studies of the summer twilight sky. It's certainly a good theory. However, one must find it difficult to accept that no one watched the twilight sky at all predating the eruption. As it turns out, there is at least one possible NLC sighting that predates the Krakatoa event by some 35 years. Dr. Christopher John Butler, a research astronomer at Armagh Observatory in Northern Ireland, who is passionate in the field of historical, meteorological and atmospheric phenomena, highlights observations recorded in the observatory's meteorological records by Thomas Romney Robinson, who was then the third director of the observatory at the time. Robinson made a series of interesting observations between 1849 and 1852. However, two of his entries in May 1850 may describe Noctilucent Clouds. On the 1st of May he notes, "Strange luminous clouds in the northwest, not auroral." This does sound very much like NLCs, even though early May falls outside the typical NLC window. However, it is not impossible, as NLCs can form at Armagh's latitude within this period. Information. An early observer of NLCs, Robert Leslie, gives a striking account of these clouds. I love this description. It goes as follows. Quote, weird small cloud forms, at times very regular, like ripple marks in sand, or the bones of some great fish or saurian embedded in a slab of stone. A marvellous description indeed, which I'm sure gave birth to the herringbone classification structure in modern times. Observing Noctilucent Clouds. Visual observations of NLCs are fairly straightforward. However, you will need to remark on a number of key factors to make your observations worthwhile for data collection. Visual observers should record the altitude of the display along with its azimuth, accompanied by brightness values and records of structure over a period of time during the apparition. An NLC season should include all of the following. Azimuths. You can measure the angular extent of the display in degrees. North is 000 degrees, east being 90 degrees, south 180 degrees and west 270 degrees. The magnitude 2 star, naked eye star, Polaris, or the North Star defines your northern point above the horizon. For example, you see an NLC display extending from the west to 10 degrees west of north. Your azimuth will be 207 degrees. It can also help to measure the full length of the display using the hand method. Hold out your hand at arm's length, spread out your fingers and try this simple technique. The distance between your little finger and thumb is 20 degrees or 40 full moon diameters. The distance between your little finger and the first finger is 15 degrees or 30 full moon diameters. Your full fist is 10 degrees. 3 fingertips are 5 degrees and your thumb is 2 degrees and your little fingertip at arm's length is 1 degree, which is equivalent to 2 full moon diameters. Altitude. Measure the angular extent, the height of the NLC display using the hand method, and if it is clear to see, measure the height of the base above the horizon, although this will not always be possible as the base can merge with other horizon, clouds or murk. Keep in mind these are simple visual observations you can do for the visual observer. You can record NLCs by descriptive records, visually or sketching or taking photographs. Here we come to the interesting part, brightness estimates. The brightness of a particular NLC display can be estimated using the official 5-point scale detailed below. New observers might find it difficult to allocate a brightness value, however with practice it will become second nature. I have used a selection of my own images to help demonstrate. However, it should be noted that NLCs can be fainter or brighter than what is shown here, so these are simply a representative example of each class. With practice you can break the rules and give a more precise estimate for your own records. For example, instead of estimating type 3, you can refine the estimate to type 3.5. Type 1 brightness. Very dim NLC present, barely brighter than the twilight background, may have the appearance of a faintly glowing white mist or fog. The fainter type 1 displays may require averted vision and are mostly missed by inexperienced observers. If you are not certain, then use a pair of binoculars and make sure the sun is between 6 and 16 degrees below the horizon using planetarium software, or get confirmation from other observers. Type 2 brightness. Clearly visible against the background twilight, but still with a relatively low surface brightness. Type 2 NLCs can manifest as a distinct blue glow against the sky, usually as a precursor to increased structure development. Type 3 brightness. This brightness level indicates a quite obvious display, standing out clearly against the background twilight. They are unmistakable. Type 4 brightness. Bright NLC, eye-catching, very easy to see and would be noticed by casual observers. Type 4 brightness is almost always associated with a spectacular display and can cast shadows on the ground. Some people have even mistaken them for a bright aurora display. Type 5 brightness. extremely bright and can illuminate buildings facing the clouds. Often Type 5 NLCs can wash out bright stars such as Capella by several magnitudes, and in extreme cases compete with the brilliance of planets Jupiter and Venus. These will impair your dark adaptation and would be seen by many with ease. I have observed Type 5 displays making fog glow bright blue, or reflecting vividly on passing tropospheric cloud, and bathing fields in their eerie light. In the past, observers could read a newspaper by their light. A Type 5 NLC display is the holy grail of the NLC observer and simply unforgettable. NLC structure classification. Each NLC season is composed with various forms of structure, of which there are 4 main types: the veil, Type 1, bands, Type 2, waves or billows, Type 3, and whirls, Type 5. Several classes are even further subdivided into other specific classes. Occasionally NLCs will possess a structure that does not fit into the 4 main groups, so another 4-point unknown category exists. See the images for examples here. An NLC display may consist of only one class or many of the classes at the same time. With a little practice, you will become proficient with matching an NLC display with its appropriate classification type. Type 1 Veil. Veil type NLC apparitions have no structure, taking the appearance of a sheet, fog or mist, and sometimes seen as a background to other forms. Seen on its own in the dead of night, the veil can look ghostly. Brightness type 3 to 5 veils are easy to see, however type 1 and 2 are often confused with the summer twilight glow by inexperienced observers. Watch out for moonlight and the twilight sky itself reflecting on high-level cirrus clouds. Can you tell the difference? Type 2 bands. These are streaks or lines which may be parallel or meet and or cross at small angles. They are further subdivided into 2 more categories. Type 3A bands. These are bands with soft edges. Bands with blurred, soft or diffuse edges similar to the edges of a comet's coma, where it may be difficult to tell where the band ends and the sky begins. This is a kind of gradual fading. Type 3B. Bands with sharp edges. Bands or streaks with sharp, well-defined edges which may be either isolated or clustered in groups. Type 3B bands look very spectacular and most striking when a shadow from a band or bands can be seen cast upon another background NLC form, which generates a very 3D-like effect. Type 3 waves. Waves are the definitive NLC structure, also known as billows or herringbone. These look like sand ripples on a beach at low tide. See Robert Leslie's description, remember, and are often seen in conjunction with Type 2A and Type 2B bands. Waves are further subdivided into 2 categories of Type 3A and Type 3. This sample image was taken of Benone Strand on the north coast of Northern Ireland during a glorious hot sunny day, while waiting for the first NLC displays of this season back in 2012. The NLC-like wave structure in the sand can be seen, which makes for a great comparison. Type 3A short waves. Type 3A waves take the form of short, straight and narrow streaks. This image taken during the active 2009 season shows these forms extremely well. You will see these waves more often than any other NLC structure. Type 3B, wave-like structure with undulations. Same as the previous type, however this time the billows may sport a wave-like structure with undulations. The extent of these undulations can vary greatly. This image was taken during 2009, during an incredible all-sky display which appeared after sunset, and with a great array of Type 3B waves on show. Type 4 whirls. Whirls consist of looped or twisted structures and are subdivided into 3 categories. by radius of the world. Type 5a, worlds with small angular radius of 0.1 to 0.5 degrees. Type 5a, worlds with small angular radius of 0.1 to 0.5 degrees. Well, these are small scale structures no larger than the apparent size of the full moon, which is half a degree. However, keep in mind that in reality these structures are located at a vast height, over 50 miles high, so in reality they would be very large indeed. This image was taken during 2011, during a nice season, late in the night, looking across the Atlantic Ocean from the County Antrim coast towards Scotland. Type 5b, simple curves with angular radius between 3 to 5 degrees. Simple curves with angular radius between 3 and 5 degrees, which is the equivalent of 6 to 10 full moon diameters. This was one of the first complex displays from the 2009 season, which had well-formed Type 5b worlds below Capella. Type 5c, large-scale worlds. Large-scale worlds with an angular extent of 10 degrees or 20 full moon diameters or more. These are my personal favourite NLC structure due to their dramatic nature. If you look carefully, you should see these worlds moving against the background stars, which can be spectacular to watch. Worlds are most often seen in very complex displays and can share the sky with a network of waves, bands and other structures, which when merged together can form very eerie forms which can look alien or even skeletal in nature. On occasion I have observed glowing spines, reptiles and even ghostly humanoid forms in a running pose. Complex structures. The complex structures fall into four main categories. Type 0, forms which don't fit into types 1 or 5, in other words unknown. NLCs which do not fit into types 1 to 5. This is the unknown category. However, it should be noted that true unknown structures are probably few and far between. It is most likely that any type 0 structure will be a combination of bands, waves, whirls, knots and nets in unison. This image was taken during June 18th and 19th, 2009 and shows the most spectacular NLC display I have ever seen so far. This was during the peak of the lowest solar minimum for a century, and from my visual records at the time I'm quite certain this contained unknown structure, some of which I have highlighted here, where several structures converge or overlap. Type S, NLCs with bright knots. Bright knots or obvious enhancements to NLC displays are normally classified as Type S. This excellent example, captured during the 2006 season with my old bridge camera, was my very first complex NLC display, and since then I have never looked back. This was taken back in the days before streetlights were introduced to my area, so I was able to photograph the display literally from my own home, back Lane in Mackara. I used an old bridge camera, my trusty Fujifilm S5600, which is proof that you don't need expensive camera gear to record NLCs. In fact, during the 2005 season, I even used a point and shoot camera on night mode, which did just as well. And modern day mobile phone cameras should do them justice too, especially the brighter displays. Why not give it a go? Type P, billows crossing a band. This display was captured during 2008, I believe. That night began cloudy, so I waited for a period indoors watching a DVD, when I suddenly got a text alert from prolific NLC observer John C. McKenna about a bright display. I grabbed my gear and ran outside, and it had suddenly cleared, so I got to the bottom of the road to record this beautiful pre-dawn show. Visually, the scene reminded me of two silvery white stallions galloping side by side through the sky from right to left. You can see the legs below and the long flowing tail behind. When I look at it now, that tail looks more reptilian in nature, like the tailbones of a velociraptor. The boxed region is a good example of billows crossing a very long band. Remember that billows are just another name for herringbone or wave structures. Type V, net-like structure. similar to a chessboard in some ways, or a fishing net. These are most likely the product of 2 or more layers of NLC overlapping, creating a pattern similar to a fishing net. In my opinion, Type V ranks among the finest examples of NLC structure possible, with the gaps in the celestial net appearing as either elongated ovals, fine squares, or in rare cases, a stunning network of diamonds. This example was taken during an all-night display from 2006. Type 5 structures are most likely to be seen when NLCs are low in the sky. When this happens, you are viewing the clouds side on at an oblique angle, so combinations of cloud have a greater chance of crisscrossing one another as opposed to the fast zenith crossing displays, which look more like single sheets and hence less likely to show complex forms. Lacunosus holes or lacunosus holes. Lacunosus is Latin for full of hollows. These lacunosus holes or pits are most often seen in mid-level and high-level weather clouds such as cirrus, cirrocumulus and even altocumulus. However, the most spectacular examples can be found within Noctilucent Clouds. Lacunosus holes are fairly common, but no less spectacular for it, with a wide range of specimens possible to observe, ranging from perfect little holes to elongated pits, to large bubbles or sharp, well-defined hoops, which at times can resemble honeycomb structure. These holes are often dramatic, arranged in clusters, and on occasion can look similar to the craters on the moon, with their floors bathed in dark shadow. This image was taken from 2011 during a very fine display. However, it wasn't the best example of these holes. Despite this, you can see that a sector of the display contains a selection of small lacunosus holes, which may have been stretched by the motion of the wave structure during the exposure. This concludes the main classification system for NLCs, and no doubt it will be revised in years to come, so thanks for reading, and I hope it helps you understand these structures in a simple, easy to understand way. The best thing to do is revise these various forms and scan through the internet and practice naming the structures you see using other NLC images, or even check out my own galleries on my website at nightskyhunter.com. With practice, you will become proficient at it. You'll be able to identify these types at a casual glance, and once you see your very own NLC display, your structure classification ability will become second nature, and with a little practice, second to none. Observing tips. Mistaken identity. High-level clouds such as cirrus cloud can easily be mistaken for NLC, especially just after sunset when low-level sun illuminates these delicate cloud strips with a gold or red colour. Watch these carefully, as cirrus will betray their identity by their normal movement and darker profile as the sun drops lower. NLCs tend to appear in the region of sky above the sun. However, formations to the east and west of the sunset point is not uncommon. 2 eyes are better than 1. Use a pair of binoculars such as 7x50 or 10x50s. Scan the twilight sky after sunset. This method can detect NLCs that would be too faint for the naked eye. NLCs differ from tropospheric cloud as they can bear magnification. Non-NLCs will have soft edges with low contrast dark profiles. However, real NLCs are unmistakable. Nlc Motion. When a large extensive NLC display is present, you will often be startled by the sudden movement of these creepy glowing clouds. Keep your eye on the bright star Capella in the north and watch the movement of the NLCs as they drift past the star. This movement is often shocking and is even more impressive in binoculars. NLCs have 2 kinds of motion. The first, watching carefully, facing north, you will notice the NLC formation drifting to the east or left in real time. This effect is due to the rotation of the Earth. Keep in mind that NLCs move at 400 miles per hour, which is as fast as a jumbo jet. And 2, NLCs will appear to either drop in height or grow in height. The mechanism responsible for this is the sun, which lurks close by under the horizon. NLC altitude will drop with a lowering sun after dusk and rise with the climbing sun before dawn. Taking several images separated by 5 to 10 minutes will show this motion easily. Often the waves or bands of a Type 5 display will occult capella as they pass, causing the star to fade and brighten like a cataclysmic variable. NLCs brighter than planet Venus, about magnitude -4.5, are not uncommon, in which case they will block out any star in that region of sky. Colour. One of the most striking visual aspects of the NLCs are their colour, which is mostly due to the position of the Sun below the horizon, producing atmospheric effects. At the horizon, which often merges with the base of NLCs, one can see red, orange, yellow, even hints of green and golden colours. Moving higher into the main body of the display, the NLCs typically sport stunning white or silver colours. The top of the display may well have the striking characteristic electric blue or purple canopy. This general blue colouring is caused by absorption of incident sunlight by ozone and the Chapius bands which reside within the yellow portion of the spectra. These colours combined together can make for a beautiful artwork against a canvas of stars. A short exposure with a camera will capture these very well. However, be careful of overexposure, which will reveal an unnatural white image. An underexposed image will capture the colours more accurately. After all, you want to record this phenomena as accurate as you can. NLC photography. NLCs are a beautiful photographic subject. Images taken of bright displays are not only satisfying, but are of use to researchers. Getting an image of NLCs is easy. However, getting a good image may be a little bit more difficult. Good images of a very bright display can be captured using ordinary off-the-shelf digital cameras. Simply attach the camera to a tripod, switch your camera to night mode or bulb setting or manual, and take short exposures. Select your low to medium range ISO setting and focus on infinity. And use your 2-second timer, 10-second timer or cable release to avoid vibration. Type 4 and Type 5 displays will be easily captured. However, the fainter displays will be rather more difficult and will involve simple post-processing techniques such as contrast, brightness and clarity to tidy the image into an acceptable result. If you do not have access to a tripod, then improvise using a windowsill, fence post or car rooftop. You can be creative. With more expensive bridge cameras or top-of-the-range DSLRs, the process is slightly different. An ISO setting between 400 and 1600 combined with an exposure from anywhere from 2 to 15 seconds, say, with a wide aperture or your aperture slightly closed down, with the timer and cable release will help reduce vibrations. You can achieve delightful results if your camera has a high optical zoom function or you have a mid-range or long-range telephoto lens. Even a 50mm f1.8 can be very useful. Zoom in close to your target area and manually focus your camera on the bright star Capella or, for example, Arcturus or any bright planet in your exposure. Some caution is required here as the NLCs may trail along with the stars, so dropping the exposure down will produce more pleasing results. These settings are meant just as a rough guide, as the NLCs themselves or the sensitivity of your camera may need very different settings. The general idea is to capture the NLC display clearly without overexposing the clouds themselves or underexposing or blowing out the sky background. Bracket your shots and you will find the perfect setting that is right for you. Try closing down your aperture slightly, for example f3.5 to f4.5 or an f2.8 lens to an f4, which can help increase contrast, sharpness and depth of focus, and on occasion even produce better colour saturation. I prefer to leave my white balance on auto. However, feel free to experiment with other settings such as daylight and tungsten, although you may find the tungsten a little bit too much on the blue side. If you shoot in RAW, then you can make these adjustments at your leisure during post-processing. This is all you need to do to capture pretty pictures, but if you would like to take images of scientific value, then you'll have to go a little bit further. Always take your images on the hour and every quarter of the hour. For example, 11 o'clock, 11:15, 11:30, 11:45 and midnight. The reason for this is very straightforward. 2 or more observers at different locations who take images at the same time will have collected enough data for triangulation, which can determine NLC height. Foreground. Selecting a suitable foreground for NLC observation and photography is important. Essentially, you'll need a clear, unobstructed horizon along the northwest, north and northeast sky sectors, as many displays are of very low altitude and which could go missed completely. A dark location away from lights is helpful, although NLCs do stand up very well to light pollution in comparison to the aurora, so bright displays can be seen exceedingly well from towns and cities. For best results, select a region of the countryside with a group of trees or small buildings to give a sense of scale. To make your images more exciting, try to include other astronomical and meteorological phenomena within the NLCs for a little bit of excitement, such as iridium flares, meteors, a rare aurora, lightning, bright comets, moonbows, fog bows, and deep sky objects such as M45, the Pleiades, M31 or Open Cluster Messier 34. If you can get a crescent moon with earthshine or a planet in the frame, then all the better. You're only limited by your imagination. Closing thoughts. Mysterious, beautiful, colourful, stunning, unpredictable and photogenic. NLCs are not to be missed, so make them a part of your life on warm summer nights. What will the next NLC season bring? Thank you very much for